So this week we're going to draw you a map for the usage of the parametric and non-parametric tests that we're going to cover in the second half of the course. So this may look somewhat intimidating, but by the end of the course this should be a pretty familiar flow chart for you. It's essentially going through your decision making when you try to get to these statistical tests. And for this week, we're going to be concentrating on this over here on the left. The assumptions that go into the test. You always have to have this independence assumption. And then these assumptions of the homogeneity of variances, additivity, and normality are all going to be assessed. And if they're violated, you'll use this branch, and if they're not violated, you'll use this branch of the tree. The differentiating feature between these two main branches is that one uses parametrical statistical tests, and the other one uses parametric statistical tests, and the other one uses non-parametric statistical tests. So parametric statistical tests are ones where you make some assumption about what the sampling distribution looks like, right? So you'll make an assumption that the sampling distribution is normal, or you'll use some sort of transformation. Maybe it'll be a Weibel or a T. It can be you can make a few different assumptions about that depending on the test that you do. But the main thing is you are making an assumption about the probability distribution. You have to make some assumption about the probability distribution. Whereas for non-parametric tests, you make no assumptions about the probability distribution function of the sampling distribution. And this is good for cases where you have non-normal data, or it's the variances are not homogeneous, or things are not additive. The non-parametric test is robust to much more. It's not as strong. You'll need bigger effect sizes and n's in order to get statistically significant different results with these tests, but it can be used for all types of data. Whereas the parametric tests have to meet these requirements before you can use them. So let's take a look at these four main assumptions for using these parametric tests. You might also note, if you've learned about the general linear model, that these are the four main assumptions of the general linear model as well, generalized linear model, but we're not going to touch on that explicitly in this course because I think it's more trouble than it's worth unless we're going to explicitly use linker functions and things like that. So we'll just keep it to, this is a good definition for when you want to use parametric tests. So the main one for both parametric and non-parametric tests is that your measurements must be independent. Independent measurements we kind of brushed on earlier when we talked about random sampling. That's one way to keep your measurements independent, right? So if I wanted to get a measurement of squirrel heights, and I just measured the same squirrel 10 times on 10 different days, and I said all of the heights are approximately the same, right? I would be violating the independence of each of the tests by taking the same squirrel over and over again, because my measurement of height on one day depended on my measurement of height on the previous day, because I was just using the same squirrel over and over again, right? So you need to make sure that each of your measurements is independent from the past measurements, right? I guess another example would be if you wanted to look at how hot a given plate was, and you measured that plate once after it had been heated, and then before letting it cool all the way, you heat it again, and then you measure it and you're like, oh, it's hotter this time. Well, it's hotter this time because it had just been heated before and you hadn't let it get back to its base state, and therefore the second measurement depended on when the first measurement was taken, and they're no longer independent of each other, right? So you want your measurements to be independent. I won't talk too much more about this. You should have a good feel for what an independent measurement is, just based on random sampling. Okay, we will talk about measurements being additive next week when we talk about linear regressions. I think it makes more sense to do that then. So for now, ignore measurements being additive. We'll address that later. And this week we'll focus instead on the sampling distributions being normal and the variances being homogeneous. So testing for normality and homogeneity of variances. So normality we looked at earlier in Module 6. These tests are all these parametric tests assume a normality of the sampling distribution, not of the data, so of the sampling distribution, and that's important because that means that because of the central limit theorem, if you have more than 50 samples, right, it doesn't really matter whether your data is normal or not, because if you have more than 50 samples, your sampling distribution is most likely going to be normal, and therefore you can use your parametric tests. However, for n's that are less than 50, we have to test using QQ plots and the Shapiro-Wilks test. We did QQ plots in Module 6. We're going to talk about the Shapiro-Wilks test here. But essentially, if your data is normal, that means your sampling distribution is going to be normal. So if your data is normal, that means your sampling distribution is going to be normal, and that means for n's less than 50, if you have normal data, you can still use parametric tests because your sampling distribution is ultimately going to be normal. So what about this homogeneity of variances? This is totally new, right? So these tests assume that all of the variances across all of your levels are equivalent. So the variance at one level, say -2, is the same as your variance at your next tested level, and that you don't get something that looks like this, where you have a variance of one kind for one level and then a very different variance for the next level. So we can test for homogeneity of variances using something called residual plots, which we'll talk about in the next slide. I will say that there are homogeneity workarounds for homogeneity of variance. So most of these parametric tests have workarounds to deal with heterogeneous variances. T-tests, instead of using a t-test, you can use Welch's t-test, which can account for heterogeneous variances. For the ANOVA, you can instead use Welch's ANOVA, which does something similar. And for regressions, you can simply transform the data, which we'll talk about if a transformation makes sense. Okay, so QQ plots is one way to assess normality. We did a bunch of these in Module 6. Refresh if you have not touched it since then, but you can use GGQQ plot or just the QQ plot built into R. GGQQ plot will give you these nice gray confidence intervals. QQ plot will not, but essentially if it plots the quantiles comparing your data to a normal curve, and if that falls on a line, that indicates that you have normal data. Okay, so for the Shapiro-Wilks test, this is a way of testing for normality if you're not really sure from the QQ plot, if it's deviates a little bit, but you don't know if that's significant. So the hypothesis here, the null hypothesis, is that the data is normal, and the alternative hypothesis is that the data is not normal. So if we reject the null, that means that we're going to have non-normal data. This test statistic here, test statistics are used for these types of tests. They're usually represented by the symbol W. I'm going to spare you the math of this particular test statistic, though we might cover some others in the future. But conceptually what this does is that it compares a value of a normal distribution that has a mean equal to your mean and a variance equal to your variance to whatever that should be in your data, right? So it's essentially like each point in the QQ plot, it sees how far that is from the one-to-one line. So it says, okay, for this particular point, if this distribution was normal, what should the value be? How far away is your data point from that actual value? And if it's further away, that leads to a larger test statistic, which ends up projecting the null hypothesis. So yeah, you're comparing what a value in the normal distribution with the mean equal to your mean and a variance equal to your variance to what your data actually is. So it's like a QQ plot, except we're doing it mathematically point by point rather than plotting it out. So this can be easily done in R using the Shapiro test function. You'll enter your data in parentheses as an array, so C open paren, data point 1, data point 2, etc. You'll put that into the test function, and then it'll spit out a test statistic as well as a p-value, and p-values less than 0.05 indicate 95% confidence that the data deviates from the normal distribution. So there's some limitations to this test. Mainly if the n is very large, it will overreact to small deviations from normality. This is true of many statistical tests because as the n gets really large, the power of the test goes up, but the effect size might be very small. So it might be a really small deviation from normality, but since the n is so large, the test detects a significant difference. But in this case, if the n is large, you probably don't care. You're not using the Shapiro-Wilks test anyway, because you can assume the central limit theorem is cleansing all of your data's non-normal sins. Okay, so let's move on to testing for homogeneity of variances. So in this case, we're going to talk about residual plots. So what are they? For categorical data, it's going to be a plot of x bar minus each one of your points, a plot of the mean minus each one of your points. And for continuous data, which we see over here, we'll cover it more in regressions, but for each value, it's how far your blue points, which are your data, deviate from the regression line, which is the red data here. Right, and so for a categorical data, they would all be in one place, and they would be going up and above and down above whatever one average is. For a linear regression, you have a slope, and therefore at each place upon the slope, you have to look at how far these things deviate. And so you'll generate a residual plot where the residuals will disperse around 0 across the level of the independent factor. In this case, negative 1.5 to 1.5. And they'll distribute evenly if you have homogeneous variances. But if you have heterogeneous variances, what you'll end up seeing is an increasing trend or a decreasing trend, where they will spread out more or decrease more as you move across the levels of the independent factor. And this would indicate that you don't have homogeneity of variances. So the way you do this in R is by calculating first your data minus x bar in the case of a categorical, or your residuals as they deviate from a line when we cover regressions. And then you'll simply plot those residuals versus the level with ggplot, data static x equals your level, y equals your residuals plus g on point, and you'll generate a residual scatter plot. So there are some alternatives that are built into R. Bartlett's test and Levine's test are available. Bartlett's test, if significance is less than 0.05, then your data has a heterogeneous variance. And you can easily just look up Bartlett's test R and figure out the function for that and the inputs. Okay, so the last thing we'll touch on today is transformations. This is, as I mentioned before, one of the ways of fixing when your variances are heterogeneous or your data is not normal. So we want the data to be linear with a homogeneous variance, but sometimes the data is skewed and variances are heterogeneous across the levels. In these cases, we have to consider data transformations. So data transformations performs one set of operation to performs a set operation on your data to transform it into a line, and then all your statistical tests can be performed on the transformed data. So, for example, right, if you were trying to do statistical tests on something undergoing exponential growth, like a bacteria or the U.S. population, right? Your data would not be linear, and if you were to plot the heterogeneity of variances versus a line here, it would not be heterogeneous. And also your data would not be normal for an exponential curve, right? So if you wanted to transform this to be a line so that you could have homogeneous variances, you could simply take the log 2 of all of your data points and then replot them. And now your data would be linear after this transformation. And you could simply perform your statistical tests on this logarithmically transformed data as opposed to your other data. And so you can do the residuals plot on your transformed data. You can do Bartlett's test on your transformed data, your test for normality, whatever it is you want to do. There are some others that you might possibly come across. You can square root, you can arc sine. Essentially, if your data follows some other easily identifiable function, you can use a function to transform it back into a line, and therefore it'll give you access to regressions and t-tests and other things that might have not been possible due to the variances not being homogeneous or your data not being normal. Okay, so we're gonna attempt all these things in the exercise this week, and I think that'll make these things pretty clear. And then next week we'll move on and start looking at regressions, which are a part of that tree, and we'll move from test to test throughout the rest of the semester.